Hello, welcome to this mini lecture on what every audio engineer needs to know about digital audio. My name is Kareem, and today our three targets will be to understand the fundamental principles of digital audio, to know what components make up a digital audio file, and to recognize concepts that are factors of digital audio. So let's start by asking ourselves the obvious question: what is digital audio? Well, simply, digital audio is technology that can be used to record, store, manipulate, reproduce sound using audio signals that have been encoded in digital formats. Now, having audio in a digital format allows for convenient manipulation and editing without destroying the original file itself. If we take, for example, a singer's voice playing into an analog electrical signal like a microphone, an analog to digital conversion takes place where the analog signal gets turned into a digital signal, i.e. a series of ones and zeros. Now, to understand a bit more about the anatomy of what makes an audio file, we need to understand the basic principles of the Nyquist-Shannon theory. So, the act of capturing an amplitude value in digital audio is called sampling. And a sample is actually just a static representation of a waveform captured in time. To capture both the positive and negative cycles of an audio waveform, we'll have to have a sampling rate that is at least double the frequency that we're sampling. If we take a sample of 20 kilohertz and a sample rate that is 20 kilohertz, we will only have one sample per completed cycle. In other words, to capture a 20 kilohertz frequency, we will need to have a sample rate of at least 40 kilohertz. Now, that basis of the Nyquist-Shannon theory then brings us to sampling rates, because the amount of samples that are taken per second is what is known as the sampling rate. With digital audio, common sample rates you'll see are 44.1 kilohertz, 48 kilohertz, 96 kilohertz. You may have even seen them already. But the higher the sample rate means we've got more samples that are taken to represent our audio. So now we know that sampling rates are the amount of amplitude values taken per second. Well, digital systems have a certain resolution on the amplitude axis, where the higher the resolution is, the more accurate our digital representation of the waveform's amplitude becomes. This is something known as the bit depth of your digital audio file. Now, increasing the audio's bit depth and sample rate, in fact, creates more total points to reconstruct the analog waveform. The higher the bit depth, the more dynamic range can be captured in our audio files. Now, a 24-bit system has a higher resolution than a 16-bit system, where a 16-bit recording has a theoretical dynamic range of around 96 decibels. A 24-bit piece of digital audio has a dynamic range of 144 decibels, which gives us basically a much higher audio quality. So now that we know what sampling rates or bit depths are, the amplitude values of an audio file are captured in a process known as quantization. Now, this is really important because the amplitude of the wave has to be fully rounded up or quantized to the nearest value that your bit depth has available. The range of possible amplitude levels are defined by the bit depth. So let's say hypothetically we had 10 numbers to represent our digital audio. Okay, and it represents, once again, the positive and negative cycles of a wave. So if our wave peaked at a value of, let's say, 8.6, then during quantization, it would be rounded up to the nearest point, which would basically be a 9, let's say. That would introduce a quantization error, which is what we don't want. And so, of course, this is a simplification because, in actuality, the possible quantization values are much closer to these numbers. And so what all that means is when we convert, we have the possibility to have certain digital audio files in certain digital audio file formats. Now, these can be divided into three main groups. We have uncompressed audio, digital audio, and you may have seen these file extensions, WAV or AIFFs. Now, if your audio files are uncompressed, they are a 100% bit-for-bit identical representation of the original work, just in digitized form. Lossless compressed audio, such as FLAC or ALAC, which is Apple's lossless. Now, these are files that are compressed, okay, so they are reducing file sizes, making them easier to store, perhaps. But on playback, they are then, once again, decoded to the original uncompressed state of the audio WAV file without degradation of the signal, which is super important. Now, I often use the analogy here where if you have a zip file and you zip your documents, of course, the documents become compressed, and so the file size decreases, okay? But as soon as you unzip or decode the zip file, your original documents are recreated with nothing being lost. So if we then move on to a lossy compressed digital file, we come to see that lossy compression has or uses digital algorithms to detect content deemed, let's say, inaudible. It does this through a variation of ways, but most of all due to something called masking, which is essentially just sounds not being heard thanks to other sounds. But critically, this information is disregarded, and we're not able to sort of take this information back. Once it's gone, it's gone. You can see that from a very nice picture we have here. Now, with all these file types in mind, an indicator of audio quality is its bit rate. And it's a measurement known as kbps or kilobits per second, where bit rate is simply just the term that we use to describe the amount of data being transferred into the digital audio file. Now, it's very easy to calculate bit rates. We take the sample rate and multiply it by the bit depth, multiplied by the number of channels. Now, the lower the bit rate, the more data essentially is just being thrown away. Okay, it's once again not possible to retrieve that data or restore it to the file once it's gone. So with all these things being said, let's move on to the pros and cons of digital audio. Now, the pros are the fact that for a number of reasons, we probably should, if we have the luxury to record with high sample rates and bit depths, we really should. And one of the main reasons, of course, is better audio quality, like we've seen. Higher bit depths and higher sample rates will always give us higher quality and higher dynamic range. Processing then becomes a lot more accurate on high resolution material. So things like equalizers, reverbs, and filters, all things for any audio engineer that they have used multiple times, I'm sure, they will sound better on higher sample rate material. And in fact, this is the reason why many plugins even include an upsampling mode, okay, where internally they work at a higher sample rate when processing the audio. Now, if we have much more samples on higher sample rates, we have a lot more accurate information about the frequencies, which means we can do really important things in the world of the audio engineer, like time stretching or pitch correction. But to finish up, we just have to briefly talk about some of the cons. Now, you do have to take note that during recording, high sample rates and bit depths will inevitably create higher resolution, but also larger audio files to work with. Now, of course, this can be pretty stressful on your hard drive space. We mentioned that to access smaller file sizes, audio bit compression is required. And once again, that's at the cost of audio quality. Now, you will have to keep in mind that if you are working on higher bit depths and resolutions, that you won't be able to add as many tracks and plugins as you are perhaps used to as an audio engineer. And so when you are working at lower sampling rates, you probably won't stress your computer out as much as you would. And hopefully you would then not see something like this, which is the dreaded overload message that your computer might throw up. And I'm sure many audio engineers have seen that. But like I said, these are all factors that are taken into consideration when considering whether or not you should work at higher sample rates and bit depths. And thanks to this mini lecture, we know what it all means when we put it together. So, hopefully you have learned something and our targets have been met. Thanks for tuning in to this mini lecture. See you soon.